The next thing we'll look at is to ask what happens when the wave hits the end of the string. The end of the string is a boundary, so what happens at the end is something we call a boundary condition. Now, there's two kinds of ends we could have on a string. The first end could be like if you have a guitar, the end is clamped down. That would be a fixed boundary. So I'll label this one fixed, where the end is clamped. Or the other choice, you could have a free end. Imagine you're grabbing something like a pool noodle or a ruler and you're shaking that up and down. The end is free to flap about. So the other choice you could have would be a free. So this is a fixed end, this is a free end. What happens when our wave hits? I've got the PhET simulation ready to go, so I'll just hit play for my fixed end. So there's my pulse going down the line. It hits, it bounces back, and it turns upside down. So that's what happens at a fixed end. It reflects and it turns upside down. What about our free end? So for this one, the wave travels down. My free end can move up and it falls back down. The wave comes back, but it stays right side up. Okay, so now we've seen our boundary conditions. Let's go on to explain them. Let's see if we can explain what happens with the fixed boundary. So as a reminder, the wave goes down and then it comes back, but it turns upside down. So let's think about what happens. And I'm going to hit pause just as it hits that boundary. Okay, there's a pause. That's not bad. So when my wave hits that boundary, the string is pulling up on the boundary. So there's the force by string on wall. Then Newton's third law tells us that if the string pulls on the wall pulls on the string. And it pulls down on it with a force that's equal and opposite. So the clamp or the boundary or the end pulls down on string. If you pull down on something, it's going to give you an upside down wave. That's why it inverts. So that's the reason it inverts. So the wall pulls down on the string and the reflected wave is inverted. Some terminology we use for this is we say that our inverted wave has a phase shift of pi. So it's out of phase compared to the incoming. So that's what happens when we have our fixed boundary. Next, we'll look at the free boundary. For our free boundary now, the wave goes down the end. So the wave gets sent down the string, hits the end, and what happens when it gets to the free end is that that free end can lift and fall back down. So free end lifts and falls. Something that lifts and falls gives an upright wave. Same thing as if your hand goes up and then down. So this is exactly the same as somebody shaking it up and then down. So in this case, it lifts up, then falls down. The up and down motion means the reflected wave is upright. We say this has a phase shift of 0, so no phase shift at all here. The next thing we'll talk about is what happens when two waves exist in the same place. What happens if two waves run into each other? If two objects run into each other, we know what happens then. Say my two water bottles, they hit each other, they collide, they bounce off. That would have been your topics of study in physics 1050 or 1020. But what about two waves? My voice talking, that's a sound wave that you can hear. What if I make another sound wave by playing music on my phone at the same time? So probably now you can hear both sounds at the same time. Two sound waves can coexist. They can be in the same place at the same time. How do we describe what happens there? Let's use our PhET simulation now to look at what happens when two waves come together. In this, I'm going to press play on my short clip. It goes pretty quickly, so I'll set it up first. I have one wave coming from the right, moving towards the left. I'll generate another wave on the left moving towards the right. They'll go towards each other, they'll interact, and then we'll see what happens. Both of our waves are upright, so we'll look at that situation first. Okay, there they come, they overlap and get big, and then they keep on going. So the wave that was going to the left keeps going to the left, the wave going to the right keeps going to the right. So while they're in the same space, they look different, but after they've passed through the same space, then they go back to what they were before. For our next one, let's look at what happens when one wave is upside down and the other is right side up. Let's see what they look like. So they pass on through. What's kind of interesting with this one is they look like they sort of flatten out. If you could hit pause at the right time, you might see that it goes exactly to 0. But we still get the same nature. The wave going to the right keeps going to the right. The wave going to the left keeps going to the left. So when they're in the same spot, they come together, they interfere and interact, but after they keep moving and they go on as if they had never met. When those waves interfere and they're on top of each other, the total wave, the new wave, is the sum of the two individual waves. That's the principle of superposition. It says that when we have two waves, let's say that the first wave is y1 as a function of position and time. The second wave is y2 as a function of position and time. Then the new overall wave that we get when those two waves are in the same place at the same time is y, depends on x and t, is y1 of x and t plus y2 of x and t. This is called the principle of superposition. When two or more waves overlap, the total displacement, so the total height of the wave relative to equilibrium, it's the sum of the displacements of the individual waves. Now we can comment a tiny bit more on the effect we observed. When the two upright waves came together, they made a new wave that was bigger. That's called constructive interference. Constructive interference whenever two waves combine to create a larger wave. So that was the first video we watched. The second video was our two waves came together and the string kind of flattened out. That's called destructive interference. So destructive interference is when two waves combine to create a new wave, and that new wave is smaller than at least one of the individual waves. And then destructive interference does have a special case of perfect destructive interference, and that happens when the two waves combine to completely cancel out. So far, we've looked at interference of waves, what happens when two waves are in the same place at the same time, where both waves are traveling waves. To look at what happens on something like a guitar string, what we have is, again, two waves. One is made by a source, and then the other waves come from the reflected end. I've got that simulated here on our PhET simulation. So I make a wave, it goes down the wave and it reflects. Now I add another wave. So this is what happens when there's just two pulses and they're interfering. What happens if the waves keep coming? What if we don't have just two pulses, but it happens over and over? We're going to look at a special case of that next.
I've come down to the first year physics lab and I've set up an experiment to show you. This is a frequency generator. It's got a piece up and down at the end that when I plug it in, it's going to vibrate up and down 120 times a second. I tied the generator onto a long piece of yellow string, which I draped over a pulley, and on the end of the pulley I hung a 200-gram mass. That provides some tension in the string. Okay, so I've got a tension. I'm about to start a frequency. I'm going to plug in my frequency generator. Maybe you can hear it going, maybe you can't. And now let's just have a look at the string. Looks like not much is going on. If I zoom right in, see how that looks all vibrating? So that is shaking up and down. There are some waves on that string, but they don't look like much. Now what I'm going to do is I'm going to change the length of the string between the frequency generator and the pulley. I'm just going to pull this string back a little bit. Now let's look at what happens to that string as I move it. Okay, not much yet. I'll keep moving it. I'll keep changing the length. Well, now something is starting to happen. Okay, so now I've moved it, and it kind of looks like my string is staying still. So right there, that's a bit that's not moving at all. And there, this is really wide, not moving at all, really wide again. So as I go along, this kind of looks like it's staying still, but my string is actually moving up and down. I can see that because if I touch it, it'll stop. Okay, so that string is moving up and down. This is called a standing wave. And to make this wave on the string, your conditions have to be exactly right. We're going to go over what those conditions are.
Now let's see what we can say about our standing waves. This is a picture of a standing wave on a string. In this particular picture, let's see how many wavelengths are on the string. So we've got a half a wavelength, a full wavelength, 1.5 wavelengths. So this specific string is 1.5 wavelengths long. We can label that in if we wish. 1 1/2 wavelengths. And this means the wavelength of the standing wave on the string because that looks like a standing wave. So if I were to draw it down below, it would look like this. So the yellow is a highlight at one point in time. I can go over it with a different color. At the opposite point in time, I can highlight this one in green. The wave goes all the way down there. And that's what makes it look like the wavelength. So we get 1.5 wavelengths there. Some places, such as right here, this is where the string wasn't moving at all. So there were no motion at these two places. And also here and here. All these places with no motion, those are called nodes. If there's no motion, the string is not going up and down at all. That's a place where there's destructive interference. Okay, now the other place that's interesting is right here and here and here. This is where the string moves the most. It goes from all the way up to all the way down. That's the most motion. That's the opposite of a node, so that's called an antinode. Since we get bigger waves there, this one is constructive interference. So our standing wave consists of more than one wave that's interfering. Some places it's destructive, some places it's constructive, and overall it looks like a standing wave. Now here's a slide with just things written out a little bit more nicely. One thing we might notice is the distance between the nodes and the antinodes. One entire wavelength looks like this. So this is one wavelength. We see that the distance between any two nodes is 1/2 of a wavelength, and the distance between any two antinodes is also 1/2 of a wavelength. We're going to go on to prove that with equations, but it's good to see first before we go on to prove it with a bunch of math. Let's look at a pretty neat example of a standing wave. If you watched the review lecture on simple harmonic motion, you would have seen this already, or you might have seen it in a high school physics class.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
Oh, okay, so let's just look at a still frame for that. I'm going to trace the line of the bridge. So there's the bridge in one frame. If we went to another frame, we would see that it looks like this. So that day on the bridge, there was actually a standing wave on that bridge where the wavelength was equal to the length of the bridge. It's actually pretty interesting. Okay, one quick example to make sure you get the idea of a wavelength before we move on. This is a standing wave, so this is comprised of two waves interfering. What is the wavelength of this standing wave? I'm going to suggest you hit pause and commit yourself to an answer, then unpause. Okay, I guess you've decided on your answer. So let's trace one full wavelength. So here's the string at one point in time, and I started at a crest. One full wavelength will take me back to a crest. So that's a full wavelength right here, from crest to crest. And according to our scale, that one full wavelength equals 1 meter. Hopefully you got the same answer as I did.